they can speak with a Russian accent. Today I will be talking about artificial intelligence in material science. And at the very beginning of science, all the knowledge was generated from experiment and observation. And scientists thought that if you perform too many experiments, too many observations, you know the truth, the ground truth about life. And it's called empirical science. Of course, it was not enough. And scientists thought that they need quantitative explanation of some phenomena. And theoretical science appeared. And they tried to make some equations to explain some effects, some processes in nature. Of course, nature turned out to be much more complex than that. And when humanity made computers, made these machines, they can go to computational science when they can simulate some processes, some materials, and presume its properties, its behavior before the experiment. And it's where predictive power comes up. And the final stage is data-driven science, because it's kind of convergence of many experiments from empirical science and computational science. So it's called the fourth paradigm. And of course, it has some main statements. You can count how many statements you consider in your research. Of course, when we talk about the fourth paradigm, it's big data. You cannot make some decent research with 2 or 10 experiments, because it's not reproducible. As you know from the articles, more than 80% of articles are not reproducible because of that. And of course, it is not representative, because when you study some materials, they can have much more unique properties than you think of. Of course, when we talk about big data, we need automatization, because you cannot perform too much experiments manually. And we talk about automated platforms for synthesis, analysis, and so on. Data sharing. If you don't have big data, it happens even in medicine, because patient data is confident. No one wants to share it, so you need some way to use all the data, but keep it local. So you don't download this data on your device, you just use it without knowing what's in it. So it's kind of optional to obtain data. Of course, data analysis. When we talk about data analysis, many of you think that you can perform data analysis. It's not true. Box plot, it's not all data analysis that can be performed on your data. And it can be misleading, and I will show you. And of course, predictive models, it's kind of next step in the computational science, but when you can either model or predict some values, some desired properties. Permanent properties. Okay. Diving into the digital material science. When we talk about big data, I will just give you some examples. You can watch the article, by the way, technology, 21st century. Just simple article, simple organic screening of several organic molecules, 1,500 reactions, and they got highly effective inhibitor of protein-protein interaction oncogenic. So they block this interaction and they can cure some types of cancer. Just big data. So they did not do any extra experiments, some extraordinary procedures, just screening. More complicated example from science. It's science. 10,000 zeolite metazoate frameworks, and they discovered 25 novel types of these frameworks, and it's science. Just screened these materials and found out that these frameworks can grow in a very complex way. When we talk about automatization, we can use it, for example, to develop some highly effective catalysts. And it's pretty much easy to track. These guys developed this tool for tracking the catalytic reaction in ultraviolet and visible spectra. And their aim was to study iridium complexes that can make a catalytic process more effectively due to homo-luma shift. And on this platform, they can see how the reaction is going in time. Also, they screened a lot of possible ligands for this kind of complexes. Simply by screening all the possibilities, all the combination between those ligands, they found out extremely effective catalytic molecules. Very simple. Of course, this can be also implemented in therapeutics. I'll just give you an example of test. They have just a lipid nanoparticle. It has various sizes, various combinations of lipid composition. They can be loaded either within the nanoparticle or on the surface of the nanoparticle. Also, it can have various amount of antigens, various amount of DNA oligonucleotides on the surface. Also, it can have different composition of these oligonucleotides. And as you can see, it's very complex problem. If you would have such a project, you will definitely screen all these possibilities by yourself. And it's not rational. And the aim of this nanoparticle was to induce immune response. And it's for cancer treatment. They developed simple protocol for screening the immune response. So they just synthesized on the microfluidic platform a lot of combinations, 1,000 combinations, and they screened them in the incubation with immune cells. These immune cells produce some molecule which amount corresponds with the immune response. And this molecule was tracked by mass spectrometry. And in such a way, they can track easily such complex process like the interaction of nanoparticles with the living cells. Also, they determined the main parameters that influence a lot this process. So they, at the end of this work, they knew how exactly to modify this platform to induce greater immune response. Now let's talk about automated robotic platforms. As you can see, it's pretty much interesting because this thing does all that you can. And it works with any kind of equipment. It makes 1,000 syntheses per week. Analyzes results in the process. So it makes experiments, see the result, makes a decision, and modifies the procedure. And not all of you can do such a thing. And it works 21 hours per day. Not all of you can do this.
Why only 21 hours per day?
Huh?
Why only 21 hours per day?
Charge. Of course, to do such a thing, you need to map all the laboratory, say to the machine where the centrifuge, where is the reactor, and so on. Also, this platform can find out what parameters influence a lot. So the more red square is, the more influent parameter is. It's very much simple. What this machine does, as you can see, it's amount of experiments. It does some basic synthesis and things like, okay, I need to modify these parameters. I need to add some more alkali. I need more L-cysteine. And as you can see, hydrogen evolution reaction, which was optimized by this machine, constantly growing with the amount of experience. And it really learns And as you can see, this is a random walk. So you just randomize parameters and try to find the best hydrogen evolution reaction. Not effect at all. Now, let's take a look at data sharing. It's really called federated learning, and federated learning is about data sharing without data sharing. So all the data persists local. So you have the data, I have the data. We can build models on our data, but you cannot know what data I have, and I cannot know what data you have. So it's kind of anonymization of data. And since all the scientists want to preserve their data, they do not want to share it with you. It's optimal solution. Of course, in chemistry, there are no many examples of this approach, but the idea starts to appear in the articles, but it's more common for medicine, actually. Now let's talk about data analysis. Of course, not all you know, but we have a lot of databases for chemists, biologists, bioinformatics, for physics, for material scientists, and we don't use it. Why? We work with similar nanoparticles, similar organic molecules, but we do not consider at all the collected data by other people. Why? Of course, there is a nanonature which contains thousands, hundreds of thousands nanomaterials with synthetic procedures, with characterization, nanoparticle size, shape, toxicity, and so on. A lot of data, and we do not use it. Of course, all of you know in CPI, a lot of data for molecular biologists. Any gene, any protein, any RNA can be found here. Of course, we have the access to work with organic synthesis, and it's a really powerful tool. And there are some algorithms that can plan your synthesis based on what you have, what do you have, what reagents, and it can give you optimal reactions with high yield, but we do not use it, actually. Why? Clinical trials it contains a lot of clinical trials of organic and nano-sized materials, and it contains a lot of side effects, biodistribution, cytotoxicity, toxicity on human, and we do not use it, but we in nanopharmacy, but we do not use it. Materials project. It's actually more about computational chemistry, and this great database with a lot of tools can help you while working with some inorganic, pretty much inorganic compounds. It has a lot of experimental and computed data like X-ray diffraction patterns, phase diagrams, melting temperature, mechanical properties, and so on. A lot of tools. And of course, we have protein data bank, very great tool to screen 3D structures of the proteins. It's assembled with some small molecules, some RNAs, and so on. Now let's talk about data mining. A lot of words. But the idea is just how do we need to work with data. Of course, when we talk about big data, it contains a lot of mistakes, a lot of typos, and you need to clean it, not manually. Because if you have hundreds of thousands samples, you cannot do it manually. So we need some algorithms to do it. Also, you need to track some dependencies, of course, not manually and with some tools. You can, based on your data, classify all the samples and then make a conclusion that, for example, you have data with 2 clusters, and in this cluster, for example, they have one property, in this cluster they have another property, and you can know that if you add some new sample in another cluster, it probably has the same property. Of course, you can get rid of some extraordinary samples, strange samples. Also, you can make a prediction. So extrapolate on new samples which are not in your data, and so on. Now let's talk about data analysis. Now, your lovely past class, very informative, because they are all similar, but the distribution is not similar at all. And the idea is you need to use Bayesian plots, which can give you so-called probability density of the samples in a particular place. So it's much more informative. So you can use it in your research. Also, you can perform so-called principal component analysis. Its idea, when you have a lot of parameters, 10, 20, and so on, you can plot all these parameters because we have only 3 dimensions, and it's not easy to analyze 3D plot. So you need somehow to preserve all the information about every sample and simultaneously to see some graph, some distribution of your samples. And the idea of principal component analysis is to squeeze the dimensions to lower the lower amount of dimensions. So you can squeeze 10 parameters to 2 parameters without sufficient loss of information. Because you need to preserve the difference between, for example, these dots. And as you can see there, the difference preserved between these samples. Also, you can perform some clustering symmetric clustering of your information. This one is called graphs. The idea is every dot on this graph is a sample, and these samples somehow, for example, these are more similar than these ones. This sample is not so similar with this one, and so on. The idea is the distance is the measure of similarity, and you can really compare your samples. And no dimension reduction technique is applied with this one, so no information loss. Of course, you can also perform so-called Cummings clustering. The idea is to find differentiable groups in your data. So there are some cases when your samples, your nanoparticles, and something else are different in some property, and you need to find out, for example, for a new sample, which property it will have if it were synthesized. But it's not really synthesized. You decide, you presume its property before the experiment. And if you perform such clustering, when the new sample occurs, for example, here, you can say that probably it will have properties similar to this cluster, samples in this cluster. Now let's talk about predictive models. I just give you several examples because this lecture is more like inspirational one. Just a brief overview of all that we have to date with artificial intelligence, chemistry, and material science. When we talk about some models, we need to think about how can I explain to computer what is molecule, what is material, how it's composed, or what elements are within this structure. And of course, you need some digital version of material or molecule. For example, actually, for small molecules, there are a lot of ways to describe it to the computer. Of course, you can actually represent it in the graphs, where each node contains the information about the electronegativity, ionic value, and so on. And the edge contains information about bond length. So it's kind of very efficient representation of the molecule. Of course, we have a lot of not so good approaches, but they still work in some ways. You can represent your molecules as a so-called bag of bonds. So the different kind of substructures of your molecule that are represented in your molecule. And of course, there are a lot of ways to represent the molecule also with full 3D geometry, but for material science, it's not so good. There are not a lot of ways to represent some crystal, some nanoparticle, even some simple nanoparticle. You can represent the simplest element of your crystal and work with it like with a small molecule, but it's kind of bad. This actually is familiar not for anyone, but it's my work. And the idea is to represent the shape, size, morphology of your particles in the image format. So you can use electron images, and from these images you can extract some features, some unique features. And with these features you can really differentiate between different materials. Now let's talk about artificial intelligence, machine learning, and deep learning. We need to differentiate between those terms. Artificial intelligence by itself is any program that can perform human tasks. Decision making, some data analysis, and so on. And it's more, it's a broader term. The subset of artificial intelligence is machine learning. And these algorithms can improve with the growth of data. So bigger data you have, greater performance is for this machine learning algorithm. And of course, you have deep learning. It's a subset of machine learning based on neural networks, which analyze pictures, which, for example, can analyze your face in your telephone, for example, can analyze some audio, some music, and so on. Different formats of data. Of course, there are many algorithms you can perform. The simplest one is called linear regression. The idea is that you have some parameters, you have some desired property, and you want, based on these input parameters, presume the final result before any experiment. But this model works only if the dependency is linear. For example, if you have two working genes, for example, and one working gene works in couple with another one, you can say that the concentration of the protein, for example, expressed by this gene, is correlated with the expression of another protein of gene 2, for example. But there are not a lot of such cases, and this model is pretty archaic. Of course, you have decision tree, and the simplest example is just imagine you have some data. For example, you have some questions. I ask you some questions, and you need to say yes or no. Just simple example. And going down to this decision tree leads you to the final result based on your answers. And it's the simplest example of how this decision tree works. But it's not perfect. What's happened? The random forest algorithm actually pretty much the same, but the idea is you have thousands of such trees, they give you a result and vote. So one algorithm says one thing, another algorithm says, no, you are not right. It's not that easy, and they vote, and the majority is the result. Just 1 millimeter down, and it doesn't work. This. Neural networks. The idea behind the neural networks is mistakenly thought to be the inspiration of the human mind, but it doesn't actually. But scientists want to, of course, mimic the human brain, but still it's even not an analogy, only the simplest one. But these algorithms can perform much better on the big amounts of data. It can analyze your faces, analyze the objects on your photographs, and so on, find some objects. And also it can make decision making. And all the robots actually can think because they have neural networks inside that can analyze some conditions, and they can make decisions based on these conditions. But of course, it has a lot of disadvantages because this algorithm can just memorize all that you given, and it's not good. So it doesn't make it doesn't make conclusions about your data. So it doesn't find any dependencies and so on. It just memorizes. But the idea in neural networks is pretty much similar to the teaching of the child. You just give them some object and say, it's a cat, it's a dog. And neural networks can differentiate between cats and dogs very easily. And the analogy is very simple. But when the neural networks fail, it means, like, for example, imagine if child memorize all the cats and dogs which he saw, and it's kind of he doesn't know what the cat is, what features it has. It just memorizes. I saw that cat. It's a cat. But if you give him new cat, he fails. Of course, I think actually I will not talk very much about algorithms because many of you actually will not do such thing, I think. Of course, we have some examples of application of machine learning and artificial intelligence, for example, in organic chemistry. Just imagine you want to inhibit some protein. And you need to find some small molecule which can inhibit this protein. What you will do? I think you will purchase this protein. You will synthesize a lot of molecules which you have in your lab, and just screen it, find the best one, and make the article. I think it will be like that. But people should, have chosen another way. For example, they need to explain the computer what is molecule. And they downloaded almost 4 million molecules and just gave them to the algorithm and said, like, it's a molecule. It's molecule 1, it's molecule 2. And this algorithm tries to understand what is molecule, what moieties it has, what groups, functional groups it can have, what is the amount of bonds for example, carbon, oxygen, and so on. And also, this algorithm, since it knows what the molecule is, can propose a new molecule. So it just gives a new molecule and says, oh, it exists. And of course, it's not the solution yet, but next step is, for example, you propose some molecules, but you need to synthesize a lot of molecules, and it's kind of hard. Every molecule is a lot of purification steps, a lot of maybe extraction, and so on. And they performed microfluidic synthesis, automated, fully automated. So we just started using the reagents, and that's all. And they had 50 precursors, 50 reagents, and their combinations can lead to a lot of molecules, possible molecules. And from molecules which were downloaded on the previous step, they have chosen those ones that can be synthesized on this platform. Of course, they proposed several synthetic pathways that they can implement on this platform, and they give the algorithm existing agonists of this protein. Just an example. So you give them all the molecules, and now you give them all the agonists of this protein, and it can really understand what makes these molecules inhibitors of this protein. And they proposed a lot of new agonists, which turned out to be extremely effective. And they proved it by a molecular token. They computed the free energy of this ligand protein interaction. Of course, artificial intelligence penetrates not only chemistry, but also in material science. For example, the idea was very simple. I need some structures which give me some spectra, infrared, visible, ultraviolet spectra. And I want to give the machine the spectrum and get the structure which I need to print to get this kind of spectrum. It's very complex, but the algorithm is to teach this machine learning algorithm to generate some images, some patterns which you need to print. as you can see, that is what algorithm proposes, and it's the ground truth. So it's kind of very similar to this one. So the machine understands how this particular spectrum can be generated from 3D structure, which would be pretty much exciting. You don't need to screen all the examples, all the variants. Of course, all these algorithms are not interpretable. So it's called black box. So you give them some input, it gives you some output, and you do not know why it decides to do this or those. And the next step in machine learning in material science is to understand how it works. So at present, we are so excited that machine learning works, artificial intelligence works, but we do not know actually how. It's just an example. These algorithms already outperform experienced physiologists, experienced doctors in their diagnosis making. So the algorithms can decide whether you have oncology or not much more effectively than doctors. With 20 amount of with 20 years of experience. The idea is pretty much simple. It's very complex, but interpretable artificial intelligence is not so easy to understand if you are not in the field, but the idea is that you can see within the structure of your algorithm why it decided to make a positive diagnosis or a negative diagnosis. Why? And it gives you I have very strange dark dot. I think it's a malignancy. So now we can see why this algorithm decides you have cancer or not. There is another term called strong artificial intelligence. The idea is the next step of interpretability of your algorithms, and you want to get some equation. You want to get some physical law. And why do we need some Einsteins when we have some algorithm which can formulate the hypothesis and make the physical law based on your data and give it to you, and you just use it. The idea is very exciting. And the hypothesis is that artificial intelligence in its final form can be such a screen, exactly a living organism which can decide. So the idea, as I said, to generate new knowledge. And it's not a black box at all, because you get some equation which explains you how your system works. And you can work with it as a chemist, as a physician, and some useful ideas. some useful reviews for you, just to dive into the topic, because a lot of works are about working with small data sets. It's all about you because you have not so many experiments, but still, for decent machine learning, artificial intelligence, you don't need too much data. You need just to work with it intelligently. So also, this review is from scratch, just from scratch. All the basic concepts of machine learning for organic chemistry and material science, also some specific organic chemistry and just high-throughput screening. So how to develop your own databases which will serve you your team and gives you an opportunity to make decent research.